So now let's discuss the molecular orbital diagrams, bond orders, bond energies, and bond lengths for several second-row homonuclear diatomic molecules, including boron, carbon, nitrogen, oxygen, and fluorine. So what these are the central parts of the orbital interaction diagrams. So energy is going up here, and we have the order that we expect of the molecular orbital, starting from the lowest energy at the bottom and going up to the highest energy. And as we deduced in the last lecture, the energies of the molecular orbitals for boron ascend thusly. We have the pi 2s, followed by the sigma 2s, followed by the pi 2p, followed by the sigma 2p, pi star 2p, and sigma star 2p. So we deduced that because boron was paramagnetic, meaning it has unpaired electrons, and that is the only way to kind of explain the order, the ascending order of those molecular orbitals' energies. We have a division here between the nitrogen and oxygen molecules, and I want you to notice that in going from nitrogen to oxygen here, the pi 2p and the sigma 2p orbitals cross in energy. So oxygen and fluorine actually have the order that we would expect if we were just deducing this from the overlap of atomic orbitals, whereas the diatomic molecules of any element lighter than oxygen have this inversion between the sigma and the pi 2p orbitals. So this is because in molecules of elements that are heavier than nitrogen, there's some interaction between the 2s and 2p orbitals of the two atoms that's not as strong due to greater energy difference between 2s and 2p. So in these lighter diatomics, it's mixing of the 2s and 2p atomic orbitals that destabilizes this sigma 2p orbital compared with the pi 2p orbital. So what's important for you guys to know is that for nitrogen and carbon and boron and any diatomic lighter than that, this is going to be the order that I expect for the MOs. For oxygen and fluorine, the order is going to be as it's shown here. So we can fill up the electrons from each atom in the molecular orbitals according to the Aufbau building up principle and Hund's rule. Now, certain definitions here. Magnetism. Any molecule that has unpaired electrons in orbitals, like boron and oxygen, is going to be labeled paramagnetic. Paramagnetic simply means that the molecule has unpaired electrons. It's going to be attracted to a magnetic field. If the molecule has all of its electrons paired up in the orbitals, it's what's called diamagnetic. So diamagnetic simply means that all of the electrons are paired and the molecule would be repelled by a magnetic field. Bond order is something that we defined in a previous lecture. We get it from taking the number of bonding electrons, subtracting the number of anti-bonding electrons, and dividing by 2. So you can calculate the bond order for each of these molecules here. And the bond order that we predict for boron and carbon and nitrogen is 1 and 2 and 3. And then for oxygen, it's 2. And for fluorine, it's 2. And in general, bond order actually corresponds to whether the bond is single, double, or triple. So boron, we would expect a single bond in the diatomic molecule. For carbon, we would expect a double bond. And for nitrogen, we would expect a triple bond. So in general, these bond orders correspond to the bond being single, double, or triple. Same with oxygen and fluorine over here. For oxygen, we would expect a double bond between the oxygen atoms, and for fluorine, we would expect a single bond. What else can we say about this? Okay, so as the bond order increases, the bond energy increases as well. You notice as the bond order goes from 1 to 2 to 3, the bond energy increases. So the higher the bond order, the stronger the bond, the more energy it takes to break it. Conversely, as the bond order increases, the bond length decreases. This makes sense because the stronger bonds mean shorter bond lengths. So the nitrogen-nitrogen triple bond, this is going to be a short, strong bond. So it has a bond order of 3, and that's kind of what we would expect to see for this one.